In this lesson, we are going to talk about the specific sampling distributions that arise for 3 of our 5 big population parameters. First, we have the sampling distribution for one sample proportion, as in the sampling distribution for p hat. So suppose we conduct a binomial experiment with n trials and success probability p. In this trial, we have successes on x of the n trials, and success might be that you have a sample and you want to figure out what proportion in that sample is female, and so success is being female. No sexism intended there, guys. The parameter we want to estimate is the population proportion p, and we estimate this using our sample by counting up how many quote-unquote successes we have, which was x. And p is estimated by p hat, which is x over n. So the number of people who have the trait which is deemed as, maybe it doesn't be success, but we call it success, divided by your sample size. So for example, suppose you sample 25 people to try to figure out what percentage of the population carries a certain allele. Let's assume that the true population parameter is 40%. The question we want to answer with these sampling distributions is how much variability will exist for your sample of n equals 25? Will you always have exactly 40% with the allele? And the answer to that question definitely is no. There will be variability among the samples. So you will not always have 40% of people in your sampling displaying that allele. And the question we want to answer is how much variability will there be? So with a sufficiently big enough sample size, a binomial random variable is approximately normal, or trials. This also applies to the proportion p hat equals x, where x is your number of successes over n. And this result can be applied in 2 different situations in which we observe categorical data. So situation 1 is that you take a random sample from a large population and you measure some categorical variable, or a binomial experiment is repeated numerous times and the proportion of success is measured. So for number 1, you could say be taking a population and taking a sample and figuring out what proportion is female in that sample. And population 2, you could say be flipping a coin 50 times and trying to see how many heads come out, which will not always be 50-50. So here is the sampling distribution for a sample proportion. P is the true population proportion of interest, or the binomial probability of success. P hat, which is number of successes divided by n, is the corresponding sample proportion, or proportion of success. If you take many samples or repetitions of size n with independent individuals or repetitions, the distribution of values of p hat, meaning the different values you're going to get for p hat, is approximately normal, with a mean of p, a standard deviation of p times 1 minus p over n, and a standard error, that's the estimate of your standard deviation. This is the square root of p hat 1 minus p hat over n. So this standard deviation tells you the true variability you're going to see in that sample proportion over samples of a fixed size. And what we're going to look at next is what happens to this standard deviation as your sample size increases. So find the mean and standard deviation of the sampling distribution of possible sample proportions for each combination of sample size and population proportion. What happens as the sample size increases? The mean here is the true population proportion, which is 0.5. The standard deviation of p hat tells us how much samples of size 400 are going to vary, and that is given by root p1 minus p over n. And note, I have standard deviation and not standard error because I know the true population proportion. So that's 0.5, 1 minus 0.5 over 400, which comes out to be 0.025. And when we increase that sample size, let's see what happens. But think about that. You're putting a bigger number in the denominator, probably going to make that standard deviation smaller. So the mean is still p, that remains unchanged. The standard deviation of p hat, same formula, just different n, 0.5, 1 minus 0.5 over 1600. So the standard deviation of p hat in this case comes out to be 0.0125. And that should jive with what, if you think about taking bigger samples, you should have less variability in those samples. You should expect to get things that are closer and closer to the true value. I mean, think about this as flipping a coin. If you flip a coin 400 times, on average you're going to probably get half heads, but there will be some variability. If you flip it 1600 times, still on average you'll get half heads, half tails, but the variability in your samples is going to decrease. So as sample size increases, the mean is unchanged, but the standard deviation of p hat decreases. A polling organization polls 100 randomly selected registered voters to estimate the proportion of a larger population that intends to vote for candidate Y in an upcoming election. Although it's not known by the polling organization, the true proportion is 0.55. This is the actual proportion that prefers candidate Y. Give the numerical value of the mean of the sampling distribution of p hat. So the mean is equal to p, which is 0.55. Find the standard deviation of the sampling distribution of p hat. Well, that's given by p times 1 minus p over n. So 0.55, 1 minus 0.55 over 100, which comes out to be approximately 0.0497. which we round to 0.05. Use the empirical rule to find values that fill in the blanks in the following sentence. In about 99.7 of all randomly selected samples of n equals 100 from this population, the sample proportion preferring candidate Y will be between blank and blank. Now remember that this occurs when you fall within 3 standard deviations from the mean. So remember that we have our mean is p plus or minus 3 standard deviations of p hat. So 0.55 plus or minus 3 times 0.05 gives us 0.55 plus or minus 0.15. So the sample proportions preferring candidate Y will be between 0.4 and 0.7. And that's a lot of variability. So with a sample size of 100, if the true population is 0.55, you'll get some samples that suggest that this person is not popular and some samples that suggest that this person is really popular. A bigger sample size would shrink this interval, and you would be able to draw better conclusions from your data. Suppose that medical researchers think that P equals 0.7 is the proportion of all teenagers with high blood pressure whose blood pressure would decrease if they took calcium supplements. This is their guess. To test this theory, the researchers plan a clinical trial or experiment in which 200 teenagers with high blood pressure will take regular calcium supplements. So first, let's assume that P equals 0.7 is actually the population proportion that would experience a decrease in blood pressure. What are the numerical values of the mean and standard deviation of the sampling distribution of P hat, the sample proportion for samples of 200 teenagers? So first of all, the mean is equal to P, which is 0.7. And the standard deviation of P hat, still given by root P 1 minus P over N. That's 0.7, 1 minus 0.7 over 200, which comes out to be 0.0324. Okay, use the results from A to calculate an interval that will contain the sample proportion P hat for about 99.7% of all samples of 200 teenagers. So using our empirical rule, we take our P plus or minus 3 times the standard deviation. So 0.7 plus or minus 0.0972. which is 0.6028 to 0.7972. So if you take many samples of 200 and you compute the proportion who experience a decrease in blood pressure from taking calcium, you would expect to see values between 0.6 and about 0.8 almost all the time. In the clinical trial, 120 of the 200 teenagers taking calcium supplements experienced a decrease in blood pressure. What is the value of P hat for this sample? Well, in this case, P hat is 120 out of 200, which is 0.6. Is this value a parameter or a statistic? Well, this is a statistic. It's taken from a sample. So, given the answers for B and C, explain why the observed value of P hat could be used as evidence that the researchers might be wrong about that 0.7. Well, notice that your interval went from, just write this down here so you can actually see it. The interval was from 0.6028 to 0.7972. That interval should contain this population proportion, the true thing, almost all the time. Specifically, 99.7% of the time, which means that there's 0.15% over here and 0.15% over there. And we have a value that's falling in this lower tail. And since that lower tail only contains less than 1%, or like less than 0.2% of the potential values, this seems unusually low. So that's what we're going to sort of write down here. The value of 0.6 is slightly below the interval of possible sample proportions. For 99.7% of all random samples of 200 from a population where p was equal to 0.7. This is unusually low. Suggesting 0.7 may not really be the true value for p. And we're going to return to that confidence interval reasoning repeatedly in this unit. Next, we're going to talk about sampling distributions for the difference in sample proportions. Sometimes we want to compare a population proportion or probability for two populations. In this case, we're going to examine the difference in two population proportions. Can you think of some examples as to when this would be an appropriate question? So one example. So suppose you want to test the efficacy of a drug. So you divide volunteers or people into two groups. Half gets the placebo, half gets the real drug. Is the proportion who recover different in these two groups? Probably specifically, is it higher with the drug versus the placebo? So to use the methods we will discuss here, you must collect independent samples. So one thing you can do is take separate independent samples from each of the two populations. So try to make sure that there aren't people that are coupled in any way, and then find the sample proportion of interest for each sample. You can take one representative sample from a population and then use some categorical variable with two categories to divide them into groups. So you could go along gender lines, take a sample, and then after you've collected some data on the sample, look at the men versus the women, or college graduates versus not college graduates, something like this. Randomly assign participants in a randomized experiment to one of two treatments, and then analyze each group. Now, the formulas for the mean and standard deviation are a teensy bit different, and the first thing we have to do is that we must assume that certain quantities are big enough. But this is, so n times p1, n times 1 minus p1, n2 p2, n2 1 minus p2. What this is ensuring is that you have at least 10 people in each of your categories. So first of all, the mean, well, much like the mean of the sampling distribution of p hat was p hat, the mean was p. This mean here is the true population proportions, just their differences. The standard deviation is a little bit more complicated. So we have standard deviation of p1 hat minus p2 hat is equal to the square root of p1, 1 minus p1 over n1, plus p2, 1 minus p2 over n2. And the standard error of p1 minus p2 hatted is when you estimate the standard deviation, and that's given by root p1 hat 1 minus p1 hat over n1 plus p2 hat 1 minus p2 hat over n2. If the population proportions are equal, what will be the mean of the sampling distributions? What this is saying is if P1 equals P2, what is the mean? Well, in this case, the mean is equal to P1 minus P2, and if those two things are equal, the mean will be 0. For each of the following situations, specify the mean and standard deviation of the sampling distribution of the difference in sample proportions. So in this case, the populations are male and female registered voters in the US, and it's of interest to compare the proportions of males and females who register with the Republican Party. So suppose in truth, 45% of men and 32% of women are registered Republicans. Random samples of 500 are taken from the population, as in each population. So we have, assuming that men are our first group, P1 is equal to 0.45, and P2 is equal to 0.32. So first of all, the mean is P1 minus P2, which is 0.45 minus 0.32, which comes out to be 0.13, meaning on average 13% more men are Republican than women. And the standard deviation of P1 hat minus P2 hat is given by the root 0.45, 1 minus 0.45 over first sample size, which is 500, plus 0.32, 1 minus 0.32, also over 500. Nothing requires that those sample sizes be the same, they just are in this case. If you're putting this in your calculator, make sure you put parentheses here and here. And you should double check that you get the same thing. You should get about 0.03. So I'd suggest pausing this and seeing if you can actually compute that correctly. For each of the following situations, so same idea, the populations are left-handed and right-handed college students. It is of interest to compare the proportions that have learned to play a musical instrument. Suppose that in truth, 35% of both populations learned to play a musical instrument, and a random sample of 500 right-handed students and 150 left-handed students will be taken. So P1 is 0.35. P2 is also 0.35. So we can say that P1 are the proportion of lefties, and P2 is the proportion of righties who have learned to play a musical instrument. The mean is P1 minus P2, or 0.35 minus 0.35, which comes up to be 0. The standard deviation of P1 hat minus P2 hat is the root P1, 1 minus P1 over N1, plus P2, 1 minus P2 over N2. Which is 0.35, 1 minus 0.35 over N1, which if we're going with N1 as lefties, that was a sample size of 150, plus 0.35 times 1 minus 0.35 over 500. This comes out to be approximately 0.044. So sample means are a teensy bit different, but the same some basic principle holds, as in larger samples produce less variability. So instead of talking about proportions, we're going to talk about means of quantitative variables. For the sampling distribution of the sample mean to be approximately normal, it's not always necessary to have a large sample. The sampling distribution of the sample mean is approximately normal in the following situations. The first situation is if the population of measurements is bell-shaped, then the sampling distribution is just approximately normal. And if the population is not bell-shaped, you just have to measure a large random sample. And our book defines large arbitrarily as having a sample size bigger than 30. So explain whether one or both of the situations for the approximate normality of the sampling distribution of the mean holds in each scenario. So mean normal body temperature will be determined for a randomly selected sample of 18 individuals. In the population of all humans, the body temperature has an approximately normal distribution with mean 98.2 and a standard deviation of 0.5. So is condition 1 met? Yes. The underlying distribution is normal. Condition 2, that our sample size be at least 30, is not met. The mean number of music CDs owned will be determined for a randomly selected sample of 4 college students. In the population of all college students, the distribution of number of CDs owned is skewed to the right. So what that means is that there's a large tail on the right. There's people who own lots of CDs, basically. So let's see, a sample of 4 college students and underlying distribution not normal. So neither condition is met. The underlying distribution is not normal. And the sample size is small. So, same idea, still talking about CDs, but now we have 900 college students. Well, condition 1 is still not met. But condition 2 is. So here is our sampling distribution for a sample mean. When a population of observations is bell-shaped and or a large random sample is taken, we define the sampling distribution to have mean mu and standard deviation sigma. Let x bar be the sample mean. Then we have that the mean is still given by the true population mean, much like in the previous situations we had that the mean was the true population proportion. Now the standard deviation of x bar, how much x bar is going to vary, is given by sigma over square root of n. And the standard error of x bar is s over root n, where s is equal to the sample standard deviation. Back in chapter 2, we found s using this formula, big old square root, sum xi minus x bar squared over n minus 1. So the weights of men in a particular age group have mean 170 pounds and standard deviation 24 pounds. If you select a random sample of 16 men, what is the standard deviation of the sampling distribution of possible sample means? How much variability are you going to see in the averages in those groups of 16? So standard deviation of x bar is equal to sigma over square root of n, which is, sigma's given us 24, for root 16, which is 4. So 24 divided by 4 is equal to 6. So that will be able to tell you, you can use the empirical rule then to say find intervals that will contain a certain 98%, 99.7% or 95% of your sample means. And if you increase your sample size, what's going to happen to this standard deviation? Well, that root n will get bigger, which will cause this standard deviation to get smaller. So the standard deviation of x bar here is still sigma over root n, so that sigma is unchanged, it's 24, but we're now over root 64, which is 8. 24 divided by 8 comes out to be 3. Larger sample, less variability in the means. So in general, how does increasing the sample size affect the standard deviation? Increasing the sample size decreases standard deviation. Of the sample mean.